What's up, folks? Going to talk about ellipses today real quick. Homework tonight, after we talk about ellipses in class, do learning guide problems number 5 through 8, but don't do the parametric part, which, I don't know, read it. It says write the equation in parametric mode. You don't know how to do that, so don't do that. But let's talk about what an ellipse is. So just like a parabola, there's a technical definition. An ellipse is a set of all points x, y, who, blah, 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 read that because I lost my track. Set of all points, the sum of whose distances from two distinct fixed points, called the foci, that is not one focus, but two foci, is constant. So what they're saying is that choose any point on here. The total combined length of those two distances from the focus to the point, that is a constant no matter where you go. So choose another point over here. That distance plus that distance is the same as that purple distance. Choose some point right here. That distance plus that distance, again, is the same as that purple distance and that green distance. So everywhere on that ellipse, the distance is constant, even if you go to a vertex right there. That distance plus then going over that and all the way there, that total distance there is the same as all those other distances. That's the definition of an ellipse. And from that, you can come up with the equation of the ellipse, which we looked briefly at before spring break. But just a couple pieces about the ellipse. First off, whichever part of the ellipse is longer, the line running between the two vertices of the ellipse is called the major axis, and the major axis will be greater than the minor axis, always, 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 and just like anything else, we always have a center smack dab in the middle. Now we need to go over a few pieces of information about the ellipse that you need to know. First off, the distance from the center to the focus is called c. You can remember it because it's the foci. So again, c is the distance from the vertex to a focus. It is a distance, so think of it as a positive number. The distance from the center, I think I said vertex, I meant to say the distance from the center to a focus. The distance from the center to a vertex is called a. That is half of the major axis, which runs from vertex to vertex. And then finally, going straight up from the center, we have b, which is the distance from the center to the co-vertex. So then if you look at the total distance from vertex to vertex, that length has to be 2a, and that is referred to as the major axis. It is the longer of the two axes. If you look at the distance from the co-vertex to the other co-vertex, that has a length of 2b, and that is the minor axis right there. So we have the major axis, it is longer, the minor axis is shorter, and that is how you should identify the ellipse as either vertical or horizontal. If the major axis is horizontal, then it is a horizontal ellipse. If the major axis is vertical, like the one to the right, then it is a vertical ellipse, and it will have a slightly different equation. Pretty much the same thing, though. But from these points, we get a very useful property, a relationship between A, B, and C. Alright, so if we choose to look at a couple special points, we can come up with a very important relationship between A, B, and C. So first off, let's pick a point that is actually a vertex. That way, when we look at the distance between that point and each focus, we can see that right there, that is the distance, let's call that D1, to the first focus. And let's think about what the value of that is. We know that bit right there is going to be this length of A minus this length of C, right? Because from there to there is A, and from there to there is C, so D1 is going to be A minus C. So let's say D1 equals A minus C. And now let's look at D2, which goes from that point, which happens to be the vertex, all the way to the other focus, which we know right here is going to have a distance sorry, let's say instead the distance from the vertex to the center right there. We know that is A, so we know that D1 is going to be A plus the distance from there to that focus, which is C. So sorry, that should be D2. D2 is going to have a length of A plus C. So then we know the constant D1 plus D2 is going to have a length of A minus C plus A plus C. And so the C's cancel out, we get A plus A. We get that the D1 plus D2 constant that is forming this ellipse is actually the length of the major axis, 2A. So we learned something very useful just by looking at the vertex as a special point. And now let's look at a co-vertex as a special point as well. So if you think of this point, if we want to find the distance from a focus to that point, we should think of this as a little right triangle. So drop that straight down. We're dealing with a little right triangle there, and we know we have the distance from the center to a focus is C, and we know that we have the distance B right there from the center to the co-vertex. So we could label the hypotenuse of this right triangle as the square root of B squared plus C squared. And if you think about it, we'd have the same exact triangle there to that other focus, and so we get another square root of B squared plus C squared. And we know that distance, again, can be thought of that constant sum of the distance from the point to each focus. And so we get the relationship 2A, which we already found to be D1 plus D2, has to equal this new distance, which is 2 times the square root of B squared plus C squared. And so I can divide by 2 on both sides, and I'm left with A equals the square root of B squared plus C squared. And if I square both sides, A squared equals B squared plus C squared, which is hugely useful to us. Looks very similar to the Pythagorean theorem, but it is not. So let's think of what this is saying. This is saying that the major, what happened? The major axis squared equals the minor axis squared plus the focal length squared. I guess some people call it the focal radius. But anyways, we have that major axis squared equals the minor axis squared plus the focal radius squared. A squared equals B squared plus C squared. And that helps us when we are looking at the equation of an ellipse, because if you look at the equation of an ellipse, it does not have a C value in it. So sometimes you'll know the focal radius and a minor axis, and you'll need to then do a little algebra to solve for the length of the major axis. Because if you look at this equation right here, we know that H and K, all that is are the coordinates of the center, just like the vertex of a parabola. So it's going to be H comma K, just like that. We know that A is going to be half the major axis, the distance from the center to the vertex A, and then B, the distance from the center to the co-vertex. So if you look at the equation for a vertical versus a horizontal ellipse, they're pretty much identical except the location of A and B. But don't feel like this is two different formulas you have to think of. Just put the larger number with the orientation of the ellipse. If it's vertical, the larger number goes with the y. If it is horizontal, the larger number goes with the x. That's the way I think of it. So again, just to summarize real quick, center at h comma k. 2a is the value of the major axis, 2b is the value of the minor axis. Your ellipse is horizontal if the larger number is underneath your x term, and the ellipse is vertical if the larger number is underneath the y term, and it's x minus h and y minus k, just like for the parabola. Now, one last term for you to know before we move forward and actually start doing some problems is a term called the eccentricity, which essentially just refers to the ovalness of the ellipse. The eccentricity E of an ellipse is given by the ratio C over A, so the focal radius divided by the distance from the center to the vertex. That tells you the eccentricity of the ellipse. Remember, A will always be the larger of the two values of A and B. And there we go. So if you picture this shape as something very close to a circle, C over A is going to be very small. I like to think of it as, if you look at that ellipse on the right, if you were to start squeezing that on its sides, the foci would move closer and closer in to the center of the circle. Think about a limit. As the foci get closer to the center, well, you get a circle there. And C would eventually go to 0, and we'd have 0 in the numerator of a fraction. So think of, again, the eccentricity as describing how far from a circle it is, and if it's a circle, the eccentricity would be 0, and a bigger number would get you farther and farther away from a circle, more elongated like the one on the right. Eventually, as you get bigger and bigger and bigger, the foci will move out from the center and get closer and closer to the vertices. And the closer they get, the closer that fraction gets to 1. And so a value of 1 would be it's never going to get there, but that value would be like the narrowest ellipse you can imagine, versus a circle would have a very, very small number, very close to 0. But all it is C divided by A, and it just describes the shape of the ellipse. So now we're going to do a few problems. The way I want this to work is for me to work a problem here, and then I'll put another problem up. You can pause the video and you can try to do the problem by yourself, and then I'll run through the explanation. I'll make a few different videos here so you can choose what to watch. I will upload this on our website as well, and then when you're done, you can go ahead and start working on that learning guide, the first few problems on there about ellipses. Problems 5 through 8. So here we go. Problem number 7 in, I believe it's chapter 12.2 in your book. No, that's a lie. 14.2 in your book on ellipses, analytic geometry. Here we go. So we're given the equation of an ellipse, x squared plus y squared equals 1, with two different denominators under x and y. We want to find the center, which I know the center will be at 0, 0, because my x and y terms don't have anything added or subtracted from them. I need to find the vertices, the foci, and the eccentricity of the ellipse, and sketch its graph. So if you look at that equation there, remember the form is x squared plus y squared. And now since the larger number is underneath the x, I know that is a squared, and then I have b squared underneath my y term. So that tells me this ellipse is horizontal, and you can think of a as being the square root of 25, which is going to be 5, and b is the square root of 16, which is 4. And so if I were sketching this ellipse, I would say my center is right there. I'd go 1, 2, 3, 4, 5. There's a vertex, 1, 2, 3, 4, 5. There's another vertex, so I can label those as 5, 0, and 0, 5 right there. That is so not how that works. My bad. -5, 0 right there. And then I would go 1, 2, 3, 4, 1, 2, 3, 4, and label the coordinates of those co-vertices. So now 0, -4, and 0, +4. And I can sketch in that ellipse to the best of my ability. Going to look something like that. Now we need to figure out where the focus is, or rather where the foci are. So remember, the major axis is equal to the minor axis plus the focal radius. A squared equals b squared plus c squared, so it's a little different than Pythag, so don't confuse it there. Be careful. And now we can plug stuff in. We know a squared is 25. We know that b squared is 16, and we don't know c squared, so we want to solve for it. So c will equal the square root of 25 minus 16, which is going to be the square root of 9. And so we know that c, the focal radius, is 3. And so we know that the foci will be in line along the major axis. And we know the focal radius is 3. So I can plot my two foci just like that, and then the coordinates are going to be a -3, comma 0, and 3, comma 0. Last thing we need to do is find the eccentricity, which is c over a. And we know that c is 3 and a is 5, so the eccentricity is 3/5. That's everything we wanted to do for that problem. I'm going to go to a new problem now, and I want you to do the exact same thing. So here you go. Here's your problem, and I want you to find the coordinates of the center, find the coordinates of the vertices, find the coordinates of the foci, find the eccentricity of the ellipse, and sketch its graph. So why don't you go ahead and pause it right here, take a few minutes to answer this. Let's say, let's just go 4 minutes on this, and then you can play through my explanation of it, and then we'll cruise from there. Alright, so to start, we should know that the center is going to have an x value of -3 and a y value of +5, coming straight from there and there, taking the opposite of those two numbers. Let's go ahead and identify this ellipse as a vertically oriented ellipse because the larger number is with your y term. So I know a equals 5, the square root of 25, which means b equals the square root of 16, which is 4. And we actually had this in the last problem, so we know this is again going to be a Pythag triple here and give us a c value of 3. But again, a squared equals b squared plus c squared, so you could solve for that in that manner. So let's go ahead and write the coordinates of the vertices. Well, the vertices will be above and below the center since it is a vertical ellipse. So take the coordinates of the center. The x value will remain the same at -3. And then the y value will increase by 3. So we'll have one vertex at -3, comma 8. And we will have a second vertex at -3, comma, go 3 below 5, which puts it at 2 right there. Same deal with the focus. We can say one focus will have that same x value, but it will be, whoops, I goofed that up. C was my value of 3. So I actually just wrote the coordinates of the two foci. So my bad, that would be foci 1 and focus 1 and focus 2. And now I want to write the coordinates of the vertices. Vertex 1, so -3. Add the length of a to that, so 5 plus 5 is 10. And then my second one at 5 minus 5, which puts it along the x-axis with a y value of 0. Let's find the eccentricity of this, which again is c divided by a. So just like the last one, it will be 3/5. And we can sketch this in real quick. The center is at -3, +5. So let's go 1, 2, 3, 1, 2, 3, 4, 5. There's my center. Now I need to go up 5 for my a value, so 1, 2, 3, 4, 5. And down 5 for my second vertex right there. Minor axis is 2 times 4, so I'm going to go over 4 to get my first co-vertex right there, and then 1, 2, 3, 4 in the other direction to get my second one. My two foci will lie in line with my major axis, which is vertical, and we already said that was at a y value of 8, and the other one at a y value of 2. So I can sketch it in like that. There we go, and we are happy. So then the only other slightly different thing you'll need to do is be able to take an equation like this and write it in standard conic ellipse form. So we will need to complete the square on both x and y. So let's go ahead and I'll show you how to do this. Then you can try one by yourself, and then you can go ahead and start working on your learning guide after that. So first thing I'm going to do is I am going to group my x terms together, 9x squared plus 36x. I am going to group my y terms together, 4y squared plus 36x. I'm being a goofy person, 4y squared minus, my bad, minus 24y, just like that. And then for the time being, I'm going to go ahead and move that 36 to the other side, by subtracting it. So 9x squared plus 36x plus 4y squared minus 24y equals negative 36. And it looks kind of goofy the way I've spaced it out, but the reason I've spaced it out like that is because we're going to be completing some squares. So first thing I'm going to do is I'm going to factor the 9 out of that x squared. So I'm going to write that as 9 times x squared plus 36 divided by 9 is 4. So x squared plus 4x right there. And now I'm going to do the same thing with my y term. Factor that 4 out. I'll be left with y squared minus 24 divided by 4 is 6y. And that all equals negative 36. And now that I have that coefficient factored out, I need to complete the square. So I'm going to leave that, I'm going to leave that 9 there. And if you look inside the parentheses, x squared plus 4x, how do we complete the square? Well, x plus, take half of that x term there, so x plus 2 quantity squared. But now you have to think, what did I add to this when I completed the square? Well, I added this 2 squared. So I added 2 squared, which is 4, but I multiplied it by 9. So I added 4 times 9 is 36. So I need to add 36 to the other side as well. And now we're going to do the same thing with our y term. So I have my 4, y squared minus 6y in parentheses. So again, look at half of that term right there, and we'll get y minus 3 quantity squared. But again, what did I add to this side to complete the square? Well, I added that 3, negative 3 quantity squared. So negative 3 squared is positive 9 times 4 is another 36. And so I can simplify this as 9 times x plus 2 squared plus 4y minus 3 squared equals negative 36. Positive 36 cancel out, and I'm left with just positive 36 right there. But this is not conic form. Conic form needs to be equal to 1. And so I'm going to divide everything by 36, just like that. And then 9 divided by 36, well, what do you know? It is 4. So I get x plus 2 squared over 4 plus 4 divided by 36. Hey, what do you know? It is 1/9. And so I'm left with y minus 3 squared over 9 equals 36 over 36 is 1. So take a look at how those numbers just played together and how we ended up with our totally factored conic form standard ellipse equation. From this, we can look and identify the center of this ellipse at negative 2, positive 3. We can identify that the larger number 9 is with the y term, giving us a equals 3. The 4 is with the x term, giving us b equals 2, the square root of that. And then we can say 3 squared equals 2 squared plus c squared. And then we can say that c equals the square root of 3 squared is 9 minus 2 squared is 4. And so we get the square root of 5 for the value of c. So now I can do everything I did before. I can write the coordinates of the vertices. V1 is going to be at the, again, the center. It's going to have the same x value because it's a vertical ellipse. So negative 2, 3 plus my half of my major axis there, a. So 3 plus 3 is 6. My second one, V2, same x value, negative 2, but it's going to be 3 down, so again on the y-axis there. And now I want to go ahead and write the coordinates of the two foci. So focus 1, again, same x value. My focal length is root 5, so I'm actually going to write this one as just 3 plus or minus the square root of 5. And that is totally fine right there. I'll just get rid of that. That's going to be both of the focuses written in the simplest form right there. Negative 2, 3 plus or minus the square root of 5. Eccentricity is going to be c, which is the square root of 5, over a, which is 3. So eccentricity equals root 5 over 3. And we could sketch this in. 1, 2, 1, 2, 3. Major axis gives us an A value of 3, so 1, 2, 3, right there, right there. B is 2, so right there, and there is our ellipse. Center, and then 2 root 5 is somewhere about there. So, do this one, and then work on your learning guide, and I'll put the answer up for you in a moment. So there you go. There's the answer for that equation. You should be able to figure everything else out by yourself to this point. So go ahead and work on your learning guide, and now I'm going to flip through a couple other problems in case you need a little more practice. You can jump back and pause and look at these problems, and I'm sure someone in the class can explain them if need be. So here you go. So write the equation using those points. Same deal, write the equation using those points. Given you the two foci and the major axis, figure it out from there, write the equation. Write the equation giving you the vertices and the minor axis length. And that should be enough for you. So go ahead and work hard, and we'll check up on this on block day. Adios.